Hi, I'm Gagan. I would like to speak about in-memory computing as part of my 8th semester seminar. The session duration will be approximately 25 minutes. So let's get started. So the agenda for this seminar will be basically first we'll get an introduction about what in-memory computing exactly is and what led to in-memory computing exactly and its advantages and various applications and uh, who are all the organizations who are trying to implement this technology today and their success stories and how exactly in-memory computing has changed the world today, and also we'll be going through applications of in-memory computing in for databases, for in business intelligence and other fields. So starting off with this introduction, what exactly is in-memory computing? In-memory computing, it is the storage of information in the RAM memory, the random access memory of dedicated servers, rather than storing data on disks and rather than storing data on relational databases which are in turn stored on disks. So by this, what we mean is that we are trying to quicken the process of fetching data from the disk. Instead of getting it from the disk, we are trying to get it from the main memory, so that it is faster. When the fetches are faster, naturally the database transactions or any kind of querying a database will be faster. So in-memory computing, we can broadly say it is more of databases and cores. The number of cores that we are running in our say our CPU. So the more number of cores, faster the transactions will be, and so obviously the database runs faster. So in-memory computing is a combination of these two. How we use the computing power available today in implementing faster databases. Okay, so moving on, let's see how the rise in how things led to in-memory computing, that is the rise of in-memory computing. So traditionally databases have been there since very long time. So previously they were being implemented on disks, that is a database and the entire RDBMS system, it is put up in the maintained in the disk, so a hard disk. So from there we used to fetch our records, or we used to query the database, and that was the process. So we know that any query or any if we try to extract or fetch data from the disk, it is faster. Naturally it is faster when compared to main memory. So what we are trying to do in in-memory computing today is maintain the database which was available in the disk in main memory. So naturally the process is faster now. So as we can see in the diagram here, the database records being fetched into the main memory, whereas in-memory computing we maintain the entire database records itself in the main memory, and whenever there is a change, there are a lot of changes that happen, or there are updates to the database, or any inserts happen, deletions happen, any kind of transactions, they are saved in the main memory, and time to time their logs are transferred into the database. There's screenshots, or we can say at intervals of certain timestamps, their images are stored into the data into the disk where they are actually stored. So in fact, by this we are making the process of fetching queries faster from the main memory instead of getting it from the disk. So here these are some of the advantages that have been mentioned here. Persistence, recovery is faster, post-processing activities also are faster, and there is always a backup to whatever we are doing in the main memory regarding the database. So the question as to why now, that is, in-memory computing is existing since very long time. It is an old idea which has come into light now. It's almost like cloud computing. What we knew that there can be such a thing done, but the implementation and it has risen now. So why now? So when we take in-memory computing in that context, the cost has a major impact. So today the cost of memory devices has fallen sharply. So we are trying to make use of that cost reduction here. So also 64-bit processors now are able to address up to 16 exabytes of data. The DRAM production costs drop by 32% every 12 months, and similarly other prices have considerably fallen in the recent times, and we are trying to make use of this point in developing in-memory computing. So we would also like to see the two phases of in-memory computing. So coming to the two phases of in-memory computing, we have hardware innovations, we have software innovations. In the hardware innovations, the latest technologies or the advancements in technology have been the multi-core architectures, massive parallel scaling with many nodes, and RAM locality being improved, and the address space 64-bit computing machines have come up, and 100 GB per second data throughput. The bandwidth increment or the speed of computing has risen sharply. At the same time, the prices of the memory devices, that is prices for RAM, are decreasing sharply, and improvement in this price performance ratio has led to in-memory computing. So software innovations, we see row and column store databases. We'll be seeing what row and column store databases are in the coming slides. Also compression, partitioning, eliminating aggregates, and avoiding expensive database operations. So there are some expensive database operations which need to be handled, like generally updates or alters and other there are some other more database operations which are expensive. So it's like we can use a simpler command instead of doing a huge larger one. Say for example, joins are generally not costly, but the way we implement. So joins, again, it depends on the way we implement. So these are the two phases or which has led to the rise in memory computing, and the innovations that we have seen which has led to such a technology today. Well, moving on, where is in-memory computing used? In-memory computing, it helps mostly in business, how an organization runs its business, and the analytics related to that, like where the company is spending a lot, whether it's R&D or it is internal costs, or the other phase where like we can check out where in which region of the world products are being sold the most and where it is low. So all such analytics occur very fast. So to quickly discern patterns of business, whether it's not just business, it need not be business, but it can be performance related matters, or it can be R&D again, like the cost being spent each year, the analytics related to that. So and perform their operations quickly in this way. Then the drop in memory prices in the present market is a major factor which is contributing to increasing the popularity of in-memory computing, as we discussed before. This has made in-memory computing economical among a wide variety of applications. So when we see, let's discuss a few applications where it is being used currently. So in-memory computing applications basically are tracing pharmaceutical packages. So worldwide there are nearly 8 billion pharmaceutical related drugs or any kind of products related to pharmaceuticals. They have a unique code and they have their own characteristics and parameters which are being tracked for each and every drug. So this leads to large amount of information that needs to be tracked overall in the whole world. So this process is made faster using in-memory computing. So once we have the data available in the database, one can run any kind of analytics. So what we say big data, right? So in that big data analytics. So big data analytics is analyzing big data. I mean analyzing huge volumes of data. So to make that process faster, in-memory computing adds on. So another example is monitoring F1 car performances. So F1 car races have huge number of parameters, I mean values being generated throughout the race every second. There are around 300 to 600 sensors which are working on the car, and they send real-time data every second. So this is continuously recorded in a database, and the parameters are analyzed in real time. Immediately data is sent back. Say any kind of analytics, say maybe he is too slow, I mean compared to the other players, or there is some problem in the wheel or the engine parameters varying. All such information is sent in real time so that the player can correct himself, or if there is a need of say any kind of repairs happening, that can also be informed to him, so that within the next before he starts the next lap, he can get it repaired or anything like that and continue the race successfully. So those are two examples that we could discuss, and we should also say that data today is of two types, basically structured, unstructured. So unstructured data is generally difficult to read through or get conclusions out of unstructured data. That task is difficult. So developing in-memory computing, the idea of developing in-memory computing is to make that task easier, making unstructured data easy to analyze. So say for example, again airplane maintenance at Boeing. So what happens, the workers, after they repair a certain part of the plane, they make reports. These reports are in the form of files. So reading through the file every time is a difficult task. So what in-memory computing does, I mean once using big data analytics, again we can go through the entire file, make conclusions out of it, get it stored in the database again. So that makes things faster. So once the database has it, it analyzes and draws conclusions out of it. Similarly, medical diagnosis also. So moving on, we have in-memory computing in the industry today. As of now, in-memory computing is one of the latest technologies that is being implemented. So some of the companies which have already adapted in-memory computing concepts basically are like social network tag.com was architected under the assumption that it will always retrieve data from the memory tier. SAP's HANA only addresses non-volatile memory. Oracle is making a similar shift with Exadata, now combining DRAM and flash into memory tier. To SAP and Oracle, the Rubicon has been crossed. In tests, HANA has processed around 1000 times more data in half the time than the conventional databases. So today we see SAP HANA courses being held in some major institutions. So it is one of the most advanced databases as of now. Oracle is, again, as we read, is working on Exadata, working on Exadata using Rubicon, its own database. So yeah, IMC will usher in an entirely new programming model and ultimately a new business model for software companies. So again, SAP HANA, it is being used by most of the companies today. especially the business intelligence companies and stock markets and all those, because of its speed and the real-time data, real-time analytics on the data it provides. So even EMC has been recently foraying into this in-memory computing technology. Moving on, the architecture, the comparison we see between memory first versus disk first architectures. Memory first architecture, we use memory as the primary storage and we use disks for backups. How we do the reading records, it is through the API call using pointer arithmetics. Here the latency is generally in nanoseconds. Disk first architecture. In disk first architecture, disk is used as the primary storage, whereas we use caches for memory transactions between the main memory and the registers. Reading records happen through API calls, that is OS input output, then through the IO controller and then to the disk. So this is obviously faster, so obviously slower, so the latency is in milliseconds. Moving on, in memory uses the first architecture, as we know, memory first architecture. Moving on, bringing computations to data. Client server, J2EE or SMP use a different model, that is, data is moved to applications for processing. Reading data not partitioned and it is stored in a central database. So it is like the application gets a query and it talks with the database and gets things done. Data sizes are relatively smaller here. It's not feasible for huge volumes of data. Technically, it is impossible to distribute computations to a central RDBMS. This is very obvious that today, as of now, RDBMS doesn't handle distributed computing or any kind of distributed computations or distributing data. It is centrally stored. So moving on, in-memory computing and Hadoop. These go hand in hand. Even as of now, today also, Hadoop and in-memory computing go hand in hand. So in-memory computing accelerates Hadoop tasks. So as we know, Hadoop and MapReduce are again a combination wherein we distribute tasks to the nodes around. In the same way, in-memory computing adds to the faster distribution of tasks and retrieval of data at those particular nodes. Computations are moved to data, that is to the individual nodes, and data is partitioned and it is stored in distributed systems. So as we know, the data is stored near the node, which data is always stored very near to the node wherever the computations related to that data are happening. So that a particular node will compute the data which is very near to it. So that data is also stored very near to the node. So data overall sizes are massive. That is why we are able to process big data today, and technically possible to distribute computations for distributed. It is technically possible. It's not like RDBMS. We can distribute data to the individual nodes wherein the computations happen related to that node. Moving on, the use cases. These are some of the use cases where in-memory computing is being used. So real-time risk analytics, any kind of risks, as we spoke about F1, any accidents, any engine problems, they are detected in real time, and analytics are done based on the data that is being collected, and a feedback is given. Similarly, the same applies here, that is real-time risk analytics. Railroad logistics. Again, railroad logistics, again to prevent accidents and also to store data regarding say production of railways or the production related to any kind of goods related to railways, or it can even actually it is true that today IRCTC is using SAP HANA as part of maintaining the IRCTC website, the millions of transactions that happen every day. So that is the reason IRCTC switched over to SAP HANA, which is an in-memory database today. so hence making the giving a better user experience to the users. Again, energy generation. Energy generation, again, there are critical parameters which have to be recorded in power generation units. So take it a nuclear plant where there are millions of parameters every second being measured to keep the system in a particular state, so that there are no accidents, it is not prone to any accidents. So energy generation again uses in-memory computing, again to process real-time data. Going on, we have oil and gas drilling. Oil and gas drilling, people sometimes, I mean, even we wondered when SAP HANA was being used in oil and gas drilling agencies. So, but actually it is very useful to them also, because there are again lot of parameters and lot of measurements, analytics, whether the pressure in the seabed where they drill oil from, all those analytics have to be stored, and they need to get results out of it and use them constructively. Again, when any organization goes on for say checking out where there are oil rigs or oil wells, to dig oil wells, there are a lot of parameters involved in that, again, to analyze and predict where there are oil reserves. So all those data being collected and analyzed, analytics being done, and results produced are really useful for the oil and gas industry as well. So by this we can see that there are wide range of uses that in-memory computing databases especially are being used today. This is the architecture of the in-memory computing technology. And we should also remember that in-memory computing is not just to databases. It is again used in cloud, Hadoop. I mean, again, in some or the other form, they again get back to databases. But we should also remember that it is not just in databases, but also other technologies like business intelligence, and in general to make transactions faster within the processor. It's not just databases, but the major application is database. So yeah, coming to the architecture, again we see the advances in hardware which have led to the rise of in-memory computing, and yeah, the 64-bit address space, the 2 TB in current server boards, 25 GB data throughput, and the cost performance ratio is declining gradually. So coming to the architecture, we generally have the row store, column store, row and the column store, the compression, the partitioning again, and the no aggregate tables. And apart from this, we should also consider the number of cores that are being placed in the processor, or the CPU, in order to increase the processor speed. So coming to the advantages, some of the advantages of in-memory computing include the ability to cache countless amounts of data constantly. This ensures extremely fast response times for searches. As we discussed before, again, the search time is drastically reduced because of in-memory computing. Again, we'll see how this is happening in the coming slides. The ability to store session data, allowing for the customization of live sessions and ensuring optimum website performance. So the ability to process events for improved complex event processing. So event processing, as we discussed in case of F1 or any real-time events happening, their data are being recorded and valuable analytics being done and valuable results being brought out, is related to this kind of event processing. Again, it's a big advantage for the world. In-memory databases. So in-memory databases, an in-memory database is a database management system that primarily depends on main memory for storing computer data. IMDBs are quicker than disk optimized databases because they carry out fewer CPU instructions, and their internal optimization algorithms are much simpler. As we saw in the previous slide, the architecture itself has some algorithms being implemented. In case of databases, there are internal optimization algorithms which make things simpler, whether it comes to indexes or whether it comes to the way the database is being stored. So optimizations algorithms are implemented. So IMDBs are mainly used in applications where response time is crucial, such as telecommunication networks, devices and mobile and networks. This is obvious, and it is the one of the main advantage of IMDBs, that is providing real-time data and real-time networks. So coming to the advantages of IMDBs, the advantages of IMDBs are as follows. The transactions are faster, the translations are fewer, that is from the query being processed, the way query is being processed, the translations that are involved are all reduced. It is as we will see in the coming slides, how the column store database makes things simpler. Multi-user concurrence, so number of users at a time can access the database without any glitches in between. And also the database is highly stable, because every time we do a transaction, an image is loaded into the disk. So we are reducing our interaction with the disk, which means it is better and highly stable. Uses of IMDB is used for developing embedded software systems like commercially off-the-shelf embedded operating systems, applications in medical devices, intelligent connected devices, commercial communication products where there is real-time data again, and transport systems, network switches, routers and set-top boxes. Routers again, they have enormous amount of data, so all that needs to be stored and analyzed, and results have to be brought out. Fulfilling the requirements of web self-service and e-commerce applications. Again, web today generates petabytes of data, and we have seen how e-commerce also generates petabytes of data. To analyze this, such a fast database, in-memory database, is very essential. Managing all real-time rating, subscribing, billing and balance information also. So this is our first use case, that is SAP HANA. Currently it is one of the most advanced databases that SAP has come up with. SAP HANA is an application that uses in-memory database technology that allows the processing of massive amounts of real-time data in a short time. The in-memory computing engine allows HANA to process data stored in RAM as opposed to reading it from the disk. This allows the application to provide instantaneous results from customer transactions and data analysis. HANA stands for High Performance Analytic Appliance, and also the architecture of HANA is very unique. When we have the general architecture of any system is like, we have the application server, then we have the web server, and in between we have the application server, and down we have the lowermost level again is our actual application or the core, the database. What SAP HANA does is it combines application server and the database together so that they interact internally and then produce results to the web server. So it is like a two-layered structure. From the three-layered we have transformed to the two-layer structure. So interactions between the layers at the same level, or say the components at the same level, same layer, is being faster. So that is what SAP HANA does. This is an overview of SAP HANA. So we have in the core we have the column and the row store and SQL interface on the column and the row store. There is lot of compression being done. The in-memory databases compress data. It's like if we have a huge amount of data, memory available, and we use very less, or we have very few bits and pieces of memory being used, there is a lot of compression that these in-memory databases do, hence reducing the storage as well as saving time in retrieving results from the database. And obviously this multi-core parallelization, which is a big advancement and advantage to in-memory computing. On the other side, we have math libraries, we have text retrieval and explorations, scripting, the application server, predictive analytics, and R integrations. Text retrieval and exploration, again, the feeds, that is the feeds from tweets or Facebook feeds, there is a lot of analysis being done on this. That is, they retrieve data from these feeds, go through the analyze. This is all done through the in-memory database or the SAP HANA. So it goes through the entire file, picks out the keywords, and from that we draw conclusions. Say the word Hinduism or extremists, or any kind of word, say, or some personality, say Obama, or any kind of celebrity whose ever name was used in more number of feeds, we can all make such analytics as well. And math libraries, we have the computation, as I said, is being done here, pushed into the database itself. So application server, the database, together they manage the computations as well. So coming to the column and the row store. So column and the row store, here in the picture we see a snapshot of database. We have the order, country, product, and the sales. In case of row order organizations, we store each row. This is a normal implementation as of today. So, but the indexes are connected in this way. So as the arrow shows, it is this way they are connected. Whereas the column store, we have the entire column being considered as one block, and this is how they are interconnected. So column at a time, so one whole column of the database at a time. So but in general, in enterprise computing, there is very less need of a person retrieving an entire row at a time. So we generally avoid retrieving the entire row or entire tuple. We generally need only a single specific value related to a particular tuple. So that is why column store databases, column order databases are more encouraged, and today this is what is being more implemented. But at the same time, it is not that row store databases are not advantageous, but it depends on the query again. So if the query requires more amount of or multiple rows or multiple values being retrieved, then we go for the row store. If it is a particular value of a particular tuple, then column order database will be more advantageous. Moving on, in-memory computing in BI, that is business intelligence. As we know today, business intelligence is a field which generally does financial analytics, the business analytics, and any kind of research or analysis related to the performance of a company, how the stocks are performing, the quarterly results, how they vary. All this come under business intelligence today. So businesses demand faster and easy access to information in order to make reliable and smart decisions. So this is very essential to any organization. Modern computers have more available disk storage than RAM, but reading data from the disk is much slower than when compared to reading data from RAM. RDBMS are designed keeping transactional processing in mind. Having a database that supports both insertions, updates, as well as performing aggregations and joins is not possible. Also, the SQL is designed to efficiently fetch rows of data, while BI queries usually involve fetching partial rows, as we discussed before, partial rows of data involving heavy calculations. So we need only a part of the a tuple or a part of a table. So in that case, we need to make our search faster. We need not go through the entire table and find out for one value. We need not go search through the entire table and fetch the value. So that is what column store database does actually. So so this slide, it actually shows why in-memory computing is very important to BI as well. Now, how in-memory computing has changed BI? The arrival of in-memory computing stored similar information together allowed storing data more efficiently and with greater compression. This in turn allowed to store huge amounts of data in the same physical space, which in turn reduced the amount of memory that is needed to perform query and increased the processing speed. So another point in memory computing, that is when we go into the inner details of what in-memory databases do, the architecture inside, apart from column store, row store databases, they also involve the algorithms which make things faster, implementing optimization algorithms. Along with them, as I said, it takes only that part of the database where changes have been made recently, say additions, deletions, such kind of things. Only which part of the database is having such alterations being done. So only that part we are making an image again. And also we store data that is related. There is another component called partitioning. Partitioning inside an in-memory database. So partitioning inside an in-memory database is what is storing similar kind of data or related data together in separate blocks. So in that way again BI has an advancement. Most in-memory tools use compression algorithms which reduce the size of in-memory data than what would be needed for hard disks. Users query the data loaded into the system's memory, thereby avoiding slower database access and performance bottlenecks. So there is query optimization also being done. With in-memory tools, data available for analysis can be as large as data mart or as small as a data warehouse, which is entirely inside memory. Since everything is in the main memory, so whether the data is large or small, an in-memory computing database can handle all kinds of data. Thank you.